In the previous video we were looking at inclined planes and basically just if an object was positioned on an inclined plane. We looked at both frictionless surfaces and surfaces with friction. In this video we're going to take it another step further forward and look at frictionless surfaces with an applied force, and then we'll also look at surfaces with friction and an applied force. So this is now sort of adding in an extra force where it could be up or down the plane. We're basically going to deal with up the plane. In the end, down the plane just means that unbalanced force acting down the plane would be larger. So we're still going to have this situation where we've got our inclined plane with our angle theta. The object's going to be positioned on the surface as per usual. The weight force acting down, so just reiterating all of these ideas. The normal force acting at a perpendicular direction. Now though we're going to have this additional force that's acting up the plane, and we're going to call that F with the subscript A for applied. So in this situation there are a couple of ways to think about this applied force. We know that a force is a push or a pull, so it could literally just be that someone's pushing it from below or pulling it from above. The applied force oftentimes though in situations that we're going to deal with, it's often going to be due to a rope or a wire, and in the case of a rope or a wire, the force that we would deal with there is known as tension. And so the idea of a tension force, it's basically just the force that exists in a wire or a rope. So that term tension is one that you need to be familiar with. Oftentimes we'll use a T instead of FA. So in this particular case, the applied force could actually be a tension force rather than just someone, say, pushing it or grabbing the object and pulling it. Now the analysis here is similar to what we saw with a surface that does have friction, given that we have this force that is acting up the plane. So it's similar to a surface with friction and no applied force. So just make that note. So we have those scenarios that we need to consider. So what I mean by that is that if we consider the situations where the parallel component of the weight is equal to and opposite the applied force, then it means that the forces are balanced, and we have a situation where the object, if it's stationary, it'll remain stationary. If it's moving at a constant velocity, it will continue to move with that velocity. So no acceleration. It's basically then an example of Newton's first law. So the object will maintain its state of motion whatever it's doing. Second scenario, again similar to what we saw with the surface with friction. If that component of the weight that's parallel to the plane is greater and in the opposite direction to the applied force, then we're going to see an unbalanced force acting. And that unbalanced force acts down the plane in this case. Now, whether you're looking at either of these two scenarios, you can always consider the sum of those two forces. So in this case, the unbalanced force is going to just be equal to W plus FA, so the vector addition of those two forces. In the first situation, the unbalanced force is 0, so we'd still have W plus FA would be equal to 0. Now there is a third situation here, so this is a little bit different now to the situation with an inclined plane with friction. The weight force could actually be less than the applied force. So that means that if we go back up to this diagram, let's imagine a situation where the applied force is really quite large, so the arrow is even bigger. You can see that that's definitely going to be larger than the parallel component of the weight that would act down the plane, and so we're definitely going to have an unbalanced force, in this case acting up the plane. So if the parallel component is less than the applied force, an unbalanced force acts up the plane. So in both of these situations with an unbalanced force, we could then apply that to Newton's second law, F equals ma, and figure out what the acceleration would be in that scenario. To put this into context, let's have a look at an example. And the situation we're going to deal with here is that an 11 kilogram object is sitting on a 47-degree slope or incline, and it has a rope attached to it. So we know straight away that there's going to be a tension involved, and in this scenario that rope is applying a force of 87 newtons. So the question would then be calculate the unbalanced force on the box. So as with most situations, I'm going to start out with a diagram. On the object. I haven't said that it's a box. So the situation that we're dealing with then, a bit of a steeper angle than the diagrams we've been looking at previously, and I've probably made that angle a bit too large, but it is a diagram, so it doesn't really matter that much. So the angle here is 47 degrees. We have the weight force acting down this way. We know that the mass of the object itself is 11 kilograms. And we know that the normal force is going to act perpendicular to that. If we represent it somewhat to scale, that's the normal force there, so it's going to be a bit smaller. And we would then also have a tension force acting up the plane that way. So there's the details of the question. We know that we also have to break the weight up into its components, so those two vectors there. So that one will be the parallel component, and that one's the perpendicular component. Again, we're not going to worry about the perpendicular component, given that it doesn't really impact the motion of the object down the incline. So there's all the details that we can gather from the question. If we then go through and solve this scenario, the first thing in most cases is just to figure out that parallel component. So W parallel is going to be equal to W sine theta, which is equal to mg sine theta. And substituting into that, we would have that the mass is 11.0, the acceleration due to gravity is 9.8. Note that we're just leaving this as a positive value in these calculations because we're dealing with down being the positive direction, and that's being multiplied by sine of 47.0 degrees. That gives us a value of 78.8 newtons down the plane. So there's the parallel component. We now need to look at the unbalanced force, and as I said before, that unbalanced force is always just going to be the addition of the parallel component of the weight and the tension force. Or tension force in this case, the applied force in a more generic sense. So we've just figured out that the weight is 78.8 down the plane. Now the tension, we're being told, or we've inferred that the tension is actually pulling this object up the plane. So that's going to be a negative value, so we're going to have to add negative 87 newtons, which gives us a value of negative 8.2 newtons. And writing that in a form that makes a little bit more sense, dealing with that negative as being up the plane, we can write that then that's 8.2 newtons up the plane. So there's the situation of an applied force with a frictionless surface. Let's now have one last look at an applied force with a surface with friction. And we're particularly going to focus on dragging an object up that surface. So we're not going to worry about applying a force down. So dragging an object up a surface with friction. And this basically now just means we have to consider what's happening with the frictional force. It's again, the analysis is going to be similar to an applied force on a frictionless incline, but we have to consider friction here as well. So if we apply a force to a frictionless surface, then we've got that that idea again of whether the force is balancing the weight or not. But the difference is the force of friction. And that frictional force now is going to be acting down the plane. So the reason why we're, like I said, specifically dealing with acting up the plane is so that this frictional force is now going to be down. I'm going to jump straight to a question here, as all of those other aspects about whether the unbalanced is up or down and all those sorts of things. We could go through and state all of that again, but to save a bit of time and to look straight at an example, we'll deal with the situation where a winch is being used to drag a car up an incline. So this incline has an angle of 14 degrees, and the situation that we're going to deal with here, there's a tension of 3,700 newtons, and the car has a mass of 1,300 kilograms. Now, what's happening in this situation, or what the rest of this question is, will determine how we go through and solve it. And the scenario that I'm going to put in front of you here is that the car is moving at a constant velocity. So that should straight away tell you something about the acceleration of the vehicle, and therefore something about the forces that are acting on it as well. And we'll go through and have a look at that. And the question then is to calculate the frictional force. Again, a good way to start is with a diagram. So we've got an incline here that has an angle of 14 degrees. Have a car positioned on that incline that looks something like that, and it's being dragged up the incline with a frictional force. So we can represent then that the car has a weight acting down. So the normal force will be acting in this direction. We know that there's a tension force that's acting up the plane, and we also need to again consider the forces that are acting on the car. I'm going to represent these in this direction this time. So that's our perpendicular component, and this one would be the parallel component. We now have to consider a frictional force that's acting in this direction, and because we know that the car is moving at a constant velocity, we know that those forces up the plane and down the plane are going to be balanced. So that's where we need to start our solution here. So constant velocity indicates that all forces are balanced. And as we mentioned earlier, that's an application of Newton's first law. So if we jot that down, so that demonstrates understanding of Newton's first law. So we can say then that the parallel component of the weight plus the tension plus the frictional force are going to add to 0. So there's no unbalanced force acting in this scenario. We know that then if we rearrange that, we're going to find that the frictional force is going to be equal to negative T minus W. So that's literally just the algebra taking those two terms across to the other side. We can then make some substitutions even further here. So the frictional force will be equal to negative T minus mg sine theta. So finding that parallel component. Keep in mind again the directions are important here, so we're going to deal with down still being the positive direction. So that tension, we need to actually substitute it in as a negative. So be careful here, we've actually got a negative of a negative. So the negative out the front is due to the moving this term across to the other side. The value of t itself will still be the negative 3,700. And if we substitute in the other quantities there, that's 1,300 multiplied by 9.8 multiplied by sine of 14 degrees. So we can then go through, calculate that, and we would find that the value is, I'll put the extra step in here, 3,700 minus 3,082. So that frictional force is a value of 600 newtons, and because it's a positive value, we know that it's down the slope, which is exactly what we'd expect, considering that the friction has to oppose the motion of the object. Now, just as one last little step here, imagine that this car was actually accelerating up the incline. That would basically mean that this tension force would be significantly larger, so something like that as an example. In that case then, we have a situation where if it was unbalanced, then we'd still have this calculation that we've shown here, except that the unbalanced force, we'd now need to know something about it because it would no longer be zero. We'd have an unbalanced force there. So maybe we would need to know something about the acceleration to allow us to calculate that unbalanced force first. But ultimately, it comes back to this idea of adding the vectors together. If they're equal to zero, it makes it a little bit easier. If they're unbalanced, then you can go through and use Newton's second law to relate back to these forces and find what the unknown quantity is, whether it's friction or tension or whatever the case may be. Hopefully that makes sense. We'll have a look at a few more of these sorts of questions in class so that you've well and truly got these ideas under control.